In the world of artificial intelligence, transformers have revolutionized how machines process and understand data, from language to images. But when it comes to graphs, those complex structures that represent relationships in data like social networks or molecular structures, applying transformers isn't straightforward. This research paper, titled Simplifying Graph Transformers by Liheng Ma and colleagues, tackles that challenge head-on by proposing a streamlined approach. At its core, the paper argues that while transformers excel in Euclidean data spaces, graphs are non-Euclidean, meaning they don't fit neatly into the grid-like formats transformers were originally designed for. The authors point out that early attempts to use transformers on graphs, like the one by Dwivedi and Bresson in 2021, didn't perform well. As a result, researchers have piled on complexities, such as integrating message passing mechanisms or inventing fancy attention systems. These additions make graph transformers powerful but also overly complicated, making it hard to borrow improvements from other transformer models in different fields. The key innovation here is that the authors go back to basics. They take the plain vanilla transformer, the simple version introduced by Vaswani and others in 2017, and make just 3 straightforward modifications. These changes allow the transformer to handle graphs effectively without drastically altering its architecture. Let's break this down step by step. First, they introduce simplified L2 attention. In a standard transformer, attention mechanisms use scaled dot product attention, which measures how similar two tokens are by looking at their dot products. But for graphs, where nodes represent tokens and edges show connections, the authors suggest using L2 attention instead. L2 attention focuses on the magnitude closeness of tokens, essentially measuring the Euclidean distance between them. This is simpler and more intuitive for graphs because it directly captures how similar or dissimilar nodes are in terms of their features, without needing extra computations. By doing this, the model can better emphasize important node relationships based on their actual distances, which is crucial for graph data. Second, they propose adaptive root mean square normalization, or RMS normalization for short. In regular transformers, normalization layers help stabilize training by scaling down the inputs. However, the authors argue that in graph settings, we need to preserve the magnitude information of the tokens, as that often carries important structural details. So, their adaptive RMS normalization adjusts dynamically to keep this information intact while still providing the benefits of normalization. This means the model can learn from the varying scales of graph features without losing key data, making it more robust for different types of graphs, like those in protein structures or social networks. The third modification is a relative positional encoding bias with a shared encoder. Positional encoding is a big deal in transformers because it helps the model understand the order and position of tokens, which in graphs translates to the arrangement of nodes and edges. Traditional methods use absolute positional encodings, but for graphs, which can be irregular, the authors opt for a relative approach. This means the encoding focuses on the relationships between positions rather than fixed spots. They also use a shared encoder, which reuses the same mechanism across layers, keeping things efficient and simple. This allows the transformer to better capture the graph's topology, its overall shape and connections, without adding bulky new components. These 3 changes might sound technical, but the paper emphasizes their simplicity. They don't require overhauling the transformer's core design. Instead, they plug right in, making it easier to adapt advancements from other domains, like language models, to graphs. To test their ideas, the authors ran experiments on a variety of graph datasets. They found significant performance gains compared to other graph transformers. For instance, their simplified model outperformed complex alternatives on tasks like node classification and graph classification, where the goal is to predict properties of individual nodes or entire graphs. This shows that you don't need fancy add-ons to achieve great results. Sometimes, less is more. The paper also dives into theoretical aspects, evaluating the model's expressiveness. Expressiveness refers to how well a model can distinguish between different graphs, almost like telling apart unique structures. Using benchmarks for graph isomorphism, they demonstrated that their modifications enable the transformer to handle this with noteworthy effectiveness. In other words, it can learn and differentiate graph patterns that might stump less capable models. One of the paper's figures illustrates this clearly. It compares different graph transformer architectures. The macro view shows how their simplified version, which they call Sargent for simplified graph transformer, fits into the overall pipeline without the extra layers seen in models like Graph GPS or GRIT. In SGT, you have the standard scaled dot product multi-head attention, followed by feed-forward networks and normalization, but with their tweaks integrated seamlessly. The broader implications are exciting. By keeping the transformer architecture simple and adaptable, this work paves the way for unifying multimodal learning. Imagine a single model that handles text, images, and graphs all at once, drawing from the same foundational design. This could accelerate progress in fields like drug discovery, where graphs represent molecular interactions, or in physics simulations, where graphs model particle relationships. The authors highlight real-world applications, referencing successes in protein structure prediction and complex simulations. They also note that their approach aligns with the ongoing push towards artificial general intelligence, where models need to be flexible across data types. In summary of their findings, these modifications not only boost performance but also maintain the transformer's generality, making it a promising step forward for graph learning. The paper was a preprint from April 2025, authored by researchers from McGill University, Mila Quebec AI Institute, Huawei Knows Arc Lab, and the University of Oxford, with Liheng Ma as the corresponding author. Throughout their evaluation, the results consistently show that simplicity can lead to sophistication, proving that elegant solutions often outperform convoluted ones in machine learning.